Okay, welcome everyone. Welcome to Geometry of Data. Um, this is the second recorded lecture that we'll have. The first one covered immersion, submersion, and basics of a neural network, what a neuron looks like, what a basic feedforward multi-layer neural network looks like, and how layers of neural networks can be understood as submersions or immersions. Right, so that was the first online lecture that we had. In this recording, what we will cover is we'll cover autoencoders and we'll cover variational autoencoders both. Okay, so we'll see what autoencoders are and then what variational autoencoders are and how these generative models connect with manifold math and how these are used in generating new data and how they represent data in a smaller, more compact representation and how this sort of all works together. Right, so this is the second lecture. We will use the slides that are already uploaded on the website, so you can get it from there. Okay, all right, let's start. So let's just start with a use case of generative models. So if you look at these images look like extremely realistic pictures of human faces. The high amount of detail and how it captures what human faces are, it's tremendous in these images. And it would be surprising if I tell you that all of these images belong to people who do not exist. So if you go to this website called thispersondoesnotexist.com, this website will automatically generate an image of a person that really does not exist in the real world. So what the model is doing is that it's using a very sophisticated autoencoder to sort of sample data from a learned distribution of human faces that it has learned using real data and is able to generate new faces that do not really exist in that data. Okay, and how does this work is that it's using a deep generative model. A deep generative model is essentially a network that takes in a random input, like a latent code. Here, the random input is just sampled from a 0 1 distribution. You can sample any latent code like this. You should be able to generate arbitrary amounts of data from generative models, which is why this latent code should be randomly sampled. So we can sample, let's say, a latent code from this normal distribution. Once we have a latent code in d dimensions, so this is d dimensions, what we do is that we pass it through a bunch of layers, neural network layers, which are represented as composition of these layers here. So it goes through G1 and then G2 and up to GL. So there are L layers in this network. And eventually what it does is it outputs a data point X, which is again in capital D dimensions. Here it would be, let's say, whatever the height of the image is, times whatever the width of the image is, and times the number of channels. The number of channels in color images are generally 3. So D here would be H times W times 3, and 3 because of RGB. Okay. So, so essentially we go from a d-dimensional latent code, a small d-dimensional latent code, which is sampled from a normal distribution, and then that gives you through transformation of neural network layers, gives you a capital T dimensional image, right? So essentially what is happening here is that this D is very small, is much smaller than the actual image that is generated, which is why we're able to sample this much easily from a normal distribution, and the model is able to sort of use that information to generate an image which is has more dimensions and is a high quality image of which belongs in the real world. Okay, right? So that is what a generative model is. Any generative model sort of should function like that. So the three things that we like, the few things that we want from a generative model are: number one, that we should be able to sample an arbitrary amount of data from the model. Number two is that the encoding should compress the data, which means that D should be smaller than capital D, which means that the latent code sort of should be smaller than the data itself. So that if you represent everything as encodings, it should be a smaller size data set than the original data set itself. So you are able to sort of compress the images into their latent codes. If you go back, like for example, if you take this image and go through a reverse of these layers, what you should be able to do is that you should be able to compress this image as a small d dimensional vector, which can then be used to recover the image, right? So it's sort of like a compression mechanism where you take an image and sort of compress it in some fewer dimensions and then use that latent code to sort of recover the image without having too much loss in the actual quality of the image. Okay, so yeah, so that is what a generative model should sort of function, should try to function as. Mhm. Okay, so now let's look at this notion of deep generative models as immerse manifolds. So, like we see in previous lectures, immersion, submersion is defined for functions that go from uh, a certain dimension manifold to a different manifold. So here, let's assume that Z belongs in this small d dimensional manifold, which is in the real space, and it goes through a composition of these individual functions, which represent each layer in the neural network, and overall composed as G goes through this G function, and then we get a data point in capital D dimensional coordinate system, which also is sort of we assume to be a manifold, right? And overall, we should have this condition that G should be differentiable, and the Jacobian matrix DG should be full rank. So if these two sort of conditions are satisfied, then we can assume that this transition function, which takes you from the latent code to the data, um, is an immersion itself, right? And then the properties of immersion also apply to these these neural network layers, right? And this can be done by checking the Jacobian matrix, like we did in the previous lecture. We were calculating the Jacobian matrix of the transition function and then seeing if it is full rank. So in this case, you should check if that Jacobian matrix is full rank, and that will give you if this is an immersion or not. Okay. In the following part of this lecture, we will mostly be talking about autoencoders and variational autoencoders, and the theory of variational autoencoders comes from this paper. It's a very important paper in generative modeling and is very influential. So I'd urge you to sort of look at this paper independently also. We will see a lot of the stuff that is mentioned in the paper, but it is always helpful for you to look at it independently and see if you were able to sort of understand much of it. Okay, so yeah, so this is what we'll be talking about. All right, so before we go to variational autoencoders, let's just see what an autoencoder is. Um, an autoencoder, what it aims to do is that you have a capital T dimensional data. Let's say we have images here. So images are again capital T dimensional, which means that should be height cross width cross 3, which is for RGB. So we have images like that, and then we pass them through a bunch of transformations, and these transformations are represented sort of are done through neural networks. So you pass them through a bunch of neural network layers, and then we get a compressed representation of the same image, right? So we have an encoding of the image, okay? And this encoding we should be such that if we pass it through a bunch of um, um, decoder neural network layers, let's say these are encoder layers because they are giving you the encoding, and these are decoder layers, neural network layers. What should happen is that the decoder neural network layer should be able to take this encoding, which is small d dimensional, and should be able to sort of recover the original image that was given to the autoencoder. So the encoding should be mappable back to the real data space and should recover an original image which was embedded as the encoding in the latent space. Right, so what essentially is happening is that we're taking an image which is in a higher dimensional capital D dimensional space, which is higher dimensions, and encoding as a small d dimension encoding, and we are able to recover this image back from this encoding using a bunch of decoder layers. So that's a very simple representation of what an autoencoder is. We will see when we see variational autoencoders how models like these are trained, but let me just give you a quick overview. What we do is that we have a large data set of images, just raw real world images. What we do is that we pass these images one batch at a time, or like one unit at a time through the autoencoder. We pass them through a bunch of encoder layers, get the encoding, and then we pass the encoding through a bunch of decoder layers and get the image back. Then what we do is that, let's say this is the image x prime and the input image is x. We compute a loss between x prime and x, and this could be any kind of loss. People have shown that L2 loss works very well, but any kind of loss between x prime and x, because you're sort of trying to make sure that the model is able to recover the signal. So any kind of discriminative loss between x prime and x should work. So what we do is that we take this as a loss, and then we find the derivative of this loss with respect to um, each parameter in the neural network and sort of optimize the neural network based on that. Okay, so we perform gradient descent um, with this loss function to optimize the autoencoder. Okay, this is yeah, basically how you would train this network, right? And we'll look at more details about how this is trained and how it is parameterized when we look at the math of variation autoencoders, and you'll be sort of able to generalize it to normal autoencoders as well. Okay. So overall, this autoencoder, this mechanism of embedding the image into a smaller, a lower dimension space and then recovering the image, is sort of like a dimensionality reduction mechanism that is represented through neural network layers. It's overall just trying to compress the data into a smaller dimensional embedding, and then is trying to recover the data from that, right? So if you recall intuitively, we understood pre-CA also as a dimensionality reduction mechanism. So the connection here is that if you only use linear activations in these autoencoding layers, like we remove all the non-linearities and we only make sure that the encoding and the decoding is done through linear transformations of the data. What will happen is that once you optimize a network like that, you will automatically recover the principal components in the latent space, right? So the model will sort of optimize to having a linear components as the principal component analysis of the data as the encoding mechanism, because that is the most convenient linear transformation based embedding of the data, and that would just give you PCA. The fact that these encoders and decoder layers have a nonlinearity makes this a little bit more complex in terms of having an embedding that is more than a PCA, right? And let's just like formally look at how it's trained. So given data x, we feed forward to get x prime output. We compute a loss between x and x prime, like I mentioned. This loss is the L2 loss between x and x prime. And then we backpropagate this loss gradient to update all the weights of the neural network, right? And yeah, backpropagation is just getting the gradient of this loss with respect to each weight in the neural network, and based on what that gradient is, you update each of the weights so that this loss can be minimized. Okay, now note that this is not a generative model, and this is a question that you should sort of pause the video and think about for a second before you move ahead. Is why is this not a generative model? And the answer to that is that this is not a generative model because this is not able to do the first thing that we want from generative models, right? The first thing that we want from generative models is that we should be able to sample an arbitrary amount of data from this model, right? And this is not possible with this autoencoder because the embeddings Z do not follow a specific structure, right? We are not able to sample a random value of Z in this small d-dimensional space, so that such that each of those Z's map to a real input. So what will happen is that if you randomly start getting values of Z from a small d-dimensional space, what will happen is that most of these values will not, a lot of these values will not map to real images. And that is because even in this small d-dimensional space, there is a manifold based on the manifold hypothesis, which sort of has all the data concentrated on it, and you can't really just sample from that manifold by sampling randomly from this d-dimensional space throughout the space, right? So because we're not able to learn such a structure in the latent embedding, we're not able to get latent codes that map to meaningful real data just by randomly sampling from a certain distribution. And because that is not possible, we're not able to generate an arbitrary image from this mechanism. What we can do is that given an image, we can find an embedding of that image and then store that embedding for later use instead of storing the image, right? So it's working as a compression mechanism, but it's not really generating new data, which is why it's not a generative model yet. Okay, so to make this a generative model, we people have come up with variational autoencoders. Okay, so variational autoencoders, let's just look at this very simply first. So what happens is that we, let's say, have an image like before in a capital T dimensional space, the image X. We then use a bunch of encoding layers to go from to go from X to get an embedding Z, right? But instead of getting the embedding Z directly, what we do is that we try to predict the mean and the standard deviation of the distribution from which this embedding Z is sampled, right? So instead of directly getting the value of Z through the encoding layers, we predict two different values using a bunch of nonlinear neural network encoding layers to sort of extract two values from this data, the mean and the standard deviation, and then using that mean and the standard deviation, we sample a value Z, which is then considered the latent code of this image, of this data X, right? And then using the Z, which is sampled from a distribution, is not really a value, a direct value anymore. We use this to pass it through a bunch of neural network decoding layers that increase the dimensionality of your embedding from again from small d dimensions back to capital D dimensions. And here what should happen is that this capital D dimension image X prime should be the same as X, like there should be minimal loss between the recovered image and the original image. The difference here is from the autoencoder is that instead of directly sort of giving us the value of Z through the encoding layers, what we are recovering is that we are recovering two different values, the mean and the standard deviation. And these mean and the standard deviation define a normal distribution from which we are to sample this latent code. So instead of directly getting the latent code as a deterministic value, we are sort of predicting a normal distribution, and from this normal distribution, we are trying to uh, extract the latent code by sampling from that normal distribution. right? So if I represent this model as like it's if I sort of draw the graphical representation of this model, um, here you'll see that the latent code Z informs X, and which is also conditioned on the parameters theta. Okay, here we know that the prior is on the Z. We will have a prior function on Z which will sort of give us a distribution that we can sample these from, and then we'll see this in the future. And we have a generator which is actually generating our data given the latent code. So the generator P theta is giving us X given Z's, right? So given the values of Z's, we are able to generate X using the parameter thetas in the neural network. So this is the generator that we'll work on. So X is essentially conditioned on Z and theta and such, right? And here the posterior that we are trying to sort of get at is just getting, like, let me see, the posterior is PZ given X, and yeah, and that is the posterior of this overall setup. Okay, yeah, we have this here. Let's look at it in a little bit more detail. Yeah, again, so we have to sample X in two steps. First, we have a prior function which tells you the distribution of all of these latent codes from which we are able to sample a Z. So we get a Z from the learned distribution of P of Z first, and then not a learned distribution, sorry, this distribution would be known as we'll see later. And from this Z, then we use a generator to pass the value of Z into the generator, which uses the parameters theta to give us a value X, right? And that X is new data. Okay, so what should happen is that every time you are sampling a Z from the prior function, it should give you a Z that should actually map to a real image. So now you can see how you can keep sampling different Z's and sort of sample an arbitrary amount of real data from this model. So this essentially now sort of is a generative model. Okay, so the analogy of the encoder here is the posterior, which is giving us Z by taking X. The X is the input, and this is the encoding. So if you look at this posterior, this is essentially the probability of getting the encoding given the input, which represents these encoding layers, right? So this is where you're getting X and then trying to predict Z. Okay, this is the representation of the encoder, and this is the generator, which is the decoder, right? So this generator represents the decoder, whereas this represents the encoder. Okay, so we have an encoder-decoder architecture which compresses images into a small d-dimensional space, and this small d-dimensional space is governed by a distribution, and then we are able to recover the image back from this small d-dimensional space. In addition to this encoding framework, we are also able to arbitrarily sample images from this model by sampling z's. Because we have a prior on z now, we can sample all the values of z that map to real data and then use those values to generate new data using the generator, which is trained using gradient descent and has neural network parameters theta, right? Okay. Okay, so now let's look at this variational autoencoder mechanism using a Bayesian perspective. So let's just use the Bayes rule to write the posterior in this case. So the posterior, as we saw, is P z given x, which can be just using simple Bayes rule can be written as Px given z times the probability of c upon the probability of x. Here, um, you can see that this is the generator of our model, which is taking our latent code z and is generating data x. And this is parameterized by theta. So this has our neural network parameters theta. And this is just the evidence, which is sort of code for the real data distribution. So P of X is just the real data distribution, and this real data distribution is generally something that we're trying to model and something that's not very easily accessible, right? And yeah, so this evidence can be sort of written as an integration over a dz as such. But what you'll see is that this integral in the denominator is intractable, which means that we are not able to sort of compute this for real cases, and this serves as a problem for us to do any reasonable inference using this autoencoder. So this is intractable and this is a problem, and let's see how we sort of work around that. And an intuition of this being intractable is that if this was intractable, if you were able to actually calculate p of x, you wouldn't be sort of doing all of this to, be able to generate data, because if you have a very accurate representation of p of x, you can just sample from that to get more and more real data. And essentially what we're trying to do is that we are trying by proxy to sample from p of x. So, which is why it's very hard to sort of directly estimate p of x. And it's reasonable that it would be intractable. And you can see the intractability in this integral form as well. When it's written as an integral with respect to dz, you'll see that this is an intractable integral, right? Okay. So before we move on, let's just look at one math concept, and that concept is called the KL divergence, or the Kullback-Leibler divergence. What KL divergence is that it's a measure of similarity between two distributions, right? So it's a measure of similarity between distributions. So given two probability distributions, what we want to estimate is that how similar these two distributions are, and that is done using the Kullback-Leibler divergence. And the Kullback-Leibler divergence is defined as such. You can see that it has this form, and what it measures is that it measures the similarity between the distribution Q and P. So, and if the Kullback-Leibler divergence between, let's say, Q and P is equals to 0, this implies that P is equal to Q, right? So these are the properties that we have. Another thing that we should note, that this divergence is not symmetric. So this means that, let me just write it out, DKL is not symmetric. And this means that the KL divergence between Q and P is not necessarily equal to the KL divergence between P and Q, right? So this is not a symmetric measure. This can be also understood as the information gained from moving from Q to P. So if you have a distribution Q and if you move to a new distribution P, the amount of information that is gained to sort of change these distributions, to bring about a change and a transformation in these distributions, is what the Kullback-Leibler divergence is trying to measure. Okay, so yeah, and it's just an expectation of the negative log of the first distribution over the second distribution, and that's how it's defined. Yeah, again, note that the Kullback-Leibler divergence between Q and P is not the same as the Kullback-Leibler divergence between P and Q, right? So this is just a measure that we'll be using in the following slides to see how we can sort of make this variational autoencoder scene a little bit more tractable. Okay. All right. So now let's use the Kullback-Leibler divergence to sort of solve one of the problems that we were having. So the problem was that our posterior that we sort of computed using the Bayesian rule, which P, Z, given X, was completely intractable because of the intractability in the denominator of the Bayes rule, right? So this made our posterior intractable. So what we will do is that we will approximate this intractable posterior with a manageable distribution of Q and Z. And by manageable, we mean that we understand what this distribution is and we are able to sort of control it better and model it better because it's just a distribution over all of our latent codes, Q of Z. So what we're trying to do is that we will approximate the intractable posterior, which was dependent on the input. Like this posterior was dependent on Z being dependent, conditioned on the input variable. We will find an unconditional distribution over the latent code as an approximation for the intractable posterior, right? So the posterior is sort of approximated by this manageable distribution, which is unconditional over the latent code, right? So once we make this approximation, what we want is that this distribution that we approximate the intractable posterior with is as close as possible to um, the posterior distribution, right? So the posterior distribution, what is being approximated, and QZ is what we are approximating it with. We compute the KL divergence between these two distributions, and we want to minimize this, right? To minimize the scale divergence, what would happen is that our approximation is more and more accurate the lower this divergence is, because scale divergence, as you recall, is just the measure of how similar two distributions are. So if these two distributions are like very similar, then the value of the scale divergence will be lower. So what we want is a lower value of scale divergence so that these distributions are close together and our approximation is sort of working, right? So let's expand the scale divergence a little bit to derive an evidence-based lower bound that we can optimize on. Okay, so the first step is just to write out the distributions in the Kullback-Leibler formula. So we just replace all the distributions, we get this. Now, using Bayesian rule within the terms here, you can rearrange it to look like this, right? And then because there's a log term, you open it up. We apply the expectation over Q to all of these terms independently. And then what we do is that we move the log P of X on one side of the equation and move all the other terms on to the other side of the equation. So when we do that, what would be left is that we will be left with the DKL, which was already on the LHS. And then we have plus um, expectation over Q of log P z comma x minus expectation over Q of log QZ, right? So let's just write these two terms as LQZ. Here you can see that LQZ is the same thing as we had written out. And this just comes from rearranging this equation, this Kullback-Leibler equation that we got. And we just write this term as LQ of Z, and this is the KL divergence. Now note that log P of X uh, is a um, sorry, log P of X is a constant value because Px is the distribution, like the real data distribution, and it does not change. So log P of X is essentially a constant, right? And because the sum of these two values is a constant, what we want is that to minimize this, what we have to do is maximize the other term, right? Because the sum of those terms is a constant. So what we want to do is minimize the KL divergence. So by proxy, what we'll do is we'll maximize this term because directly optimizing the KL divergence is difficult. So instead of minimizing the KL divergence directly, we will maximize this other term And because the sum of these two terms is a constant value, which is the log of the real data distribution, what would happen is that by proxy, we would be minimizing the KL divergence and making our approximation more and more accurate. Right, so this gives us an evidence lower bound that we need to optimize over. So we have the evidence lower bound LQ of Z as this, and this is what we're trying to optimize so that the KL divergence is being optimized by proxy. Okay, all right. Right, so now let's sort of look at the graphical representation of the variational autoencoder so far. So now we have the encoder network, which is also parameterized by neural network parameters phi, and this is neural network param parameters. So we're using neural network parameters to take in the input value x, which is an observed uh, value. This is observed in the real data, and given the observed data, we get an encoding variable using the encoder network. We pass it through a bunch of layers, get the encoding variable z, and then the decoding network, which has parameters theta, gives takes in the encoding variable z. This is the encoding, and then tries to recover the actual data from it, right? So the decoder network is decoding the Z representation back to the image, right? And what we are trying to do is we are trying to maximize this elbow that we saw on the previous slide. I've just written this Q of Z now and replace that with our encoder network, and the encoder network, as you recall, is also conditioned on X. So yeah, so we just replace log q of z with log q of z given x, which is what we use as the encoder network, and the other network is just the decoder network, and this is the joint probability distribution of x and z with respect to that decoding network, right? Okay, so now let's sort of expand this a little bit more so that we can. Okay, so now we need to maximize the elbow. Let's write out what the elbow looks like in while after expanding it. So this is what the elbow is. We expand the first term using again the Bayes theorem to log of p theta z plus log of p theta x given z, um, just because log of p theta z, no, sorry, p theta z times p theta x given z is equals p theta x comma z, right? Just very simply using Bayesian rule, Bayes rule, and replacing these two. Then this is the same as above. We rearrange all the terms, and then sort of what happens is that the this elbow breaks down into two individual distinct terms that we can optimize. The first one is just the KL divergence between this distribution, which takes in the value x and gives us z, i.e. the encoder network, and the distribution of all z's. So the KL divergence between these two. And the second term is just the expectation over q phi of this log p theta x given z, which is the decoder network, right? To recall. Now the problem here again is of interactability. Because we want to optimize these using gradient descent, we need to calculate gradients with respect to all the parameters phi and theta. What happens is that if you're trying to optimize the parameters phi, which is the parameters of the encoder network with respect to maximizing this term, what happens is that the gradient of this is intractable, right? So this again is a problem with the interactability. So because this gradient is intractable, we have to use something called a Monte Carlo approximation. And this approximation is done by sampling different values of z from the distribution of z. Instead of computing it in general, we compute it by sampling. So we compute sort of sample a bunch of z's from this distribution that we know, and then from And then we compute all of these values individually, and the average value of this sort of sampled latent codes is what the approximation of this gradient term is estimated to be, is assumed to be. So let me just sort of quickly tell you what the Monte Carlo trick is so that that step becomes clearer. Okay, so the Monte Carlo trick. And this is a side note, but you don't really need to understand like each step of this math. Just know what are the mathematical concepts that we are using and why we are doing each of these things. Okay, so let's say this is something that you want to compute, like this is the gradient that you would want to compute over a function f of z. So, right, the function is over z and the expectation over is over q uh, with five parameters of z, and we need to calculate the gradients with respect to the parameters phi, right? So this can be also written as we're taking the expectation inside, uh, sorry, expectation outside the gradient calculation step. So this can be written as e q phi of z, and the f of z goes inside, and the gradient with respect to log of q phi z, right? So this is just like a rearrangement of terms. Now this, based on the Monte Carlo trick, can be approximated as 1 by L, where L is the number of Z's that you sample for this approximation. Because this approximation is based on sampling, so you do Monte Carlo sort of sampling L different values of Z, and then compute this as an approximation of those values in discrete values that we compute, right? So this is just a summation over 1 over L of f of C, and then compute the gradient C, the sth Z. Sorry, let's say the ith Z, right? And this I, as we know, goes from 1 to L, and log q phi z I, right? So we sample a bunch of z's, and then we compute this for each of the z's, and then like an average of those values is what is the estimation of this term that we want to estimate, like this gradient, right? So that is what the Monte Carlo trick is. So if we apply that trick as we see it here, and we assume that f of c is the function that we want, which is again this function, if you use that, this is what you will get. Okay, so using the Monte Carlo trick, we sort of circumvent this interactability situation that we have with this gradient, and we are able to approximate that gradient as like an average of individual gradients that we calculate with respect to different values of z that we sample from the distribution. Okay, yeah, so that's how the Monte Carlo approximation leads to um, circumventing this interactability. All right, another thing that we have to optimize is the other term, right? So we only looked at this term so far. This is the term that we also need to optimize to maximize the elbow overall, right? So now let's look at the other term, right? So the other term is just this minus scale divergence between these two distributions. What it says in normal, like English, is that the encoder should make a code Z, and the Z should look like the prior distribution. Okay, so what this should do is that when we are encoding the image X into the latent space as Z, the encoding should look like it's part of a prior distribution that we have over Z, right? And the prior distribution is sort of represented as p theta of z, which is the distribution of all the z's that we are considering, and that's the prior. What should happen is that this distribution should be as close as possible to the conditional distribution, which is the encoder, and the Kerr divergence between these should be minimized. But how do we do that? Because we're not really able to sort of compute what this p theta of z um, is is not computable. So instead of directly doing that, what we do is that instead of directly encoding the value z, we encode the parameters for a normal distribution. Like we discussed in the first slide, what we do is instead of directly getting z, what we do is we sort of using our encoder framework, instead of directly predicting the distinct values, mean and the standard deviation, and the mean and the standard deviation sort of define a normal distribution from which these z needs to be sampled, right? So instead of directly modeling the latent code, we are modeling a distribution from which the latent code needs to be sampled, and this we choose this distribution of the latent code to be a normal distribution with the mean mu and the standard deviation pi square, and these two are the things that we will be sort of predicting from the encoder. So the encoder will give this as the output, the mu and the standard deviation. Okay, so let's look at how this works. Yeah, so we are sort of approximating this encoder distribution of the AI with uh, means and standard deviations for each xi. So for each xi, there will be a different mean and a different standard deviation that the encoder would give you. And given that mean standard deviation, what we would want is that um, if we sample a value z from it, that sampled value should sort of recover the original image x that was sort of embedded as this distribution. So every image is sort of not just getting embedded as one point, it's just getting embedded as a distribution, and from any point in that distribution, we can sample this data back. Okay, and what we assume is that the distribution of z is a normal distribution, is a standard normal distribution centered around zero with standard deviation one. Yeah, so now that we have assumed that this a normal distribution, this should follow the prior distribution should be a standard normal distribution, and this we do because if we know what the prior distribution is, we can sample more and more values of z from that prior distribution and then use those values to sort of generate more data. So that is what we wanted, right? We wanted from a generative model to be able to sort of sample a large number of z's randomly from a distribution, and for each value of these z's, we should be able to map it back to the real data distribution, get some real data, right? So because we sort of assume our prior to be a normal distribution, now we can sample arbitrarily from this. And now this, because we know what both of these distributions sort of look like, the encoder distribution is parameterized as a standard normal distribution, which is centered at mu, which is predicted by the model, and the standard deviation is sigma, which is also predicted by the model. And the other distribution is a normal distribution, which is centered around zero, and the standard deviation is one. The KL divergence between these two is has a closed form because these are both normal distributions. So if you look up on the internet what the KL divergence between two normal distributions look like, you will exactly get this formula, right? So the first distribution is this, and the second distribution is this. If you replace all the means and the standard deviations in that formula with the means and the standard deviations that we know here, you will get this form of the KL divergence between these two normal distributions, and you will see that this is very easily optimizable because all of these mu and the standard deviations will be predicted by the encoder framework and will depend on the parameters, um, encoder parameters, and hence, because these encoder parameters are generating these values, we can use backpropagation to sort of optimize the scale divergence and optimize the parameters of the encoder as well. All right. Yeah. So we have sort of circumvented the problems we had for both of these terms now, and this elbow can now be optimized nicely. Okay. And by optimizing this, we can learn a strong variational autoencoder from which we can sample images. And once you do that, what happens is that if you interpolate between the latent codes of, let's say, a number 7, like this is the MNIST dataset. So what you do is that we train a variational autoencoder on MNIST dataset. MNIST dataset is a dataset of handwritten digits. So it has a bunch of images of handwritten numbers by a large number of people. And what we do is we train an autoencoder, a variational autoencoder on these digits. And what you will see is that if you interpolate between the encoding uh, of the number 7 and the encoding of the number 1, right? If you interpolate from here to here, you will see how this number sort of kind of smoothly transforms into the other number. It's not exactly a smooth transition, but a variational order encode sort of is trying to learn a latent space where the intermediate steps between two latent codes also make sense, right? And this can be seen much better in these images. So if you train an autoencoder only with a reconstruction loss, you will see that in the latent space, these images are sort of embedded like this. This is the representation of the latent space. What happens is that if you try to sort of go from this number 1 to this number 7, you will see that there is a tremendous lack of data in the intermediate steps. So these intermediate steps will not really map back to a real number, and this interpolation will sort of break down. Okay, but in the case when you sort of try to uh, only optimize over scale divergence, which is essentially what it's trying to do is that is trying to make sure that the latent representation follows a unit normal distribution, right? Um, so you'll see that all of your latent codes sort of follow a normal distribution, which is centered and goes out like this, like this. I'm drawing a contour map. So you can see that the distribution does follow a normal distribution because we are trying to optimize over KL divergence only, which means that we are trying to make sure that the latent representations follow uh, 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 this distribution and 0 1 distribution. And if we only optimize between using the KL divergence, what will happen is that only the latent codes will have a normal distribution. But these normal distribution does not really make any sense because you see that these numbers are not really separated out, and all of these numbers are sort of jumbled together because you're not really decoding these numbers back to images. So they do not really arrange themselves you following any logic. They just randomly arranged so that all of them just follow a normal distribution. And then when we use both of these losses, the reconstruction loss that the autoencoder uses and the KL divergence loss as well, you will see that the latent embeddings will automatically sort of arrange themselves in a logical fashion where similar numbers are encoded in similar part of the latent representation. So all the numbers which are represented by this light green dot, which is let's say 0, are embedded further away from numbers like 1, right? Which are all embedded together. And also you'll see that because this embedding, sorry, these representations are so dense, what would happen is that if you try to interpolate between a number, let's say 2 to a number 1, you will see that you are able to recover images that make way more sense as a transition from 2 and 1, right? So the image will sort of smoothly map from going changing from looking like 2 and looking like a 1, right? So and numbers that look similar to each other relatively are embedded closer. So, for example, like these purple dots are 7, and these yellow dots, as we see, are 1. So, because 1 and 7 sort of look similar, you see that in the latent representation also they are sort of embedded close to each other with a lot of overlap between the numbers. Whereas 0 and 1 don't really look as similar, so they are embedded further away. Whereas 0 and this number 6, both of which have curves, are sort of embedded close together and have some bit of overlap. So you see this kind of a structure being learned in the latent space automatically when you use the KL divergence laws as well as the reconstruction laws. And the KL divergence loss is making sure that all of these representations together sort of follow a normal distribution. So that if we sample from that normal distribution anywhere in this space, you will be able to recover an image from it. Okay, unlike an autoencoder where there is no sampling distribution, so we can't really pick a value from this latent representation. What would happen is that if you pick a random value like this, will not really map to any point. Okay, and now because we know what the normal distribution is, and this is, let's say, let me draw a contour plot of the distribution. Maybe the distribution is looks like something like this. Because we know what the distribution is, we can sample values from this distribution, and most of these values will sort of map back to real images. All right, so that's how a variation autoencoder works, and that's the use of using a variation autoencoder to be able to generate large